I'd like to start today's talk with a familiar story. You've been spending your day writing some code, and you've committed your work and pushed it up to GitHub or your favorite source code host of choice. You create a pull request, and you think, I'll go grab a coffee, wait for someone to review that, and then you get to carry on with your day. Today's going all right. And then you get a call from, oh, I've not got slides up there yet. This is actually worth rewinding for, at least for impact on this slide. You get a call from your least favorite person, and there's a screenshot of PagerDuty giving you a phone call there, which everyone loves. Hey, that's all we got. And you sigh, and you put down your nicely steamed milk in the corner, you make the coffee later, whatever. And you get to your desk, you open the dashboard, and you see something like that. All of the responses from your API are errors, they're 5xx. Your system's fallen on the floor. And when you look into your error tracker, you see that every error in there is saying that your app couldn't connect to the database because the database is down. And today we're going to look into an incident that was just like that. But before we get going, hi, my name is Chris. In my spare time, I like to post ridiculous selfies on the internet. If you would like to reach me on the internet, you can go to sinjo.dev and send messages on your preferred social media. During the day, I work as an infrastructure engineer, which is kind of a mixture of writing software and doing typical systems work. And in particular, databases and distributed systems are the thing I've chosen to do with my career. I quite enjoy it. And so it probably doesn't surprise you that I've ended up working at a database as a service company. So I work at PlanetScale. We do a managed sharded MySQL thing. It's very cool. But today's talk is actually about the job I had before this at GoCardless, where one of the things I was responsible for was the Postgres cluster that stored all of the authoritative data about our payments. We were a payments processor. So the idea of the talk is that we're going to look behind the scenes of something we often take for granted, something run by somebody else, the primary database. And we're going to explore the aftermath of a complex outage of a Postgres cluster, the Postgres cluster that we depended on. And to give you the highest level outline of what our cluster looked like, it was a fairly standard setup. We had an API backend. In our case, they were Ruby on Rails. They were talking to a primary Postgres server. That primary Postgres server replicated its data off to two more Postgres servers. And we ran a piece of software called Pacemaker on each of those servers to handle failing over between them in the event of hardware breaking. We also had a virtual IP address, which would be co-located at all times with the primary. This was so that clients could be shifted around. I realize this is quite old school now, but there are cloud primitives that are essentially the same thing. So, let's say the primary fails, Pacemaker notices and demotes it. One of the replicas gets turned into a new primary, and we move the virtual IP address so that all of the Ruby on Rails apps go and do their writes to the new primary. The application only sees a short interruption from this as it makes that reconnection. And one important thing to note is that one of these two replicas is always synchronous with the primary. And what that means is that before the primary says, yes, I've got that right, it makes sure that the data is actually on that replica as well. This is important for data durability, and it becomes relevant a little bit later in the tale. So keep that in your mind. So unfortunately, as you may have guessed by the fact that I am stood here on stage today, on the day of the incident, none of that worked. At 3:09 in the afternoon, the RAID controller on the primary node failed pretty hard. It logged that 3 of the 4 disks in the RAID 10 array had simultaneously disappeared and been ejected. That shouldn't matter, though, because in theory, Pacemaker should handle it. It should say, this has failed, and I'm going to shift all of our write traffic over to this synchronous replica. Except that it didn't. And we made a ton of attempts to kick it back into action. We went in and cleared its error cache. It has something that stores the errors it's seen. We restarted a bunch of parts of it, but nothing was happening. And all the while, our API was down. So in the end, we fell back to a fully manual setup. One of our team logged into the synchronous replica, promoted it to be the turned off Pacemaker so that it wouldn't take any actions now that we were doing things manually, promoted that node to primary, pushed a config change to the API servers to tell them to no longer talk to the virtual IP, because that was managed by Pacemaker, which is off now. And once we were back up, they bootstrapped a new third node in case we had another hardware failure while we were recollecting our thoughts. So we were safe for now, but we had a completely unmanaged cluster, and we were only one failure away from more downtime, which was not really acceptable as a payments company. So at this point, we had to get back to a state where we had our cluster automation running, and we wouldn't be vulnerable to that kind of failure again. So we had one mission, which was to recreate the outage, which is what we're going to look through today. And there's a lot involved, but we're going to take it step by step, and I promise you that none of it will get too big brain at any point. So we're going to look at 5 events that we put back together by looking through logs and metrics from the day. The first thing that kicked it off was the RAID array losing those disks. The second thing we noticed from the kernel logs was that the kernel immediately set the file system to read-only. Reading from those disks, frankly, was wishful thinking at that point. The RAID array was gone. Pacemaker detected, in fact, it did detect that the primary failed, but for some reason, unknown to us at the time, it didn't kick off that failover. We noticed that in the logs of the synchronous replica, one of its sub-processes had crashed at the time as well, just after the primary. And when that happens, Postgres restarts the entire, restarts all of its sub-processes and itself to ensure that it's in a consistent state. And the last thing we noticed was that on the synchronous replica, there was this kind of weird, suspicious log line, something about an invalid record length. Sorry, that's the next slide. So this weird, suspicious log line. So we've restored some log file from an archive somewhere, and it's complained that one of the lengths of some record that's been written there is invalid. It felt suspicious, but we didn't really know what this meant in Postgres terms at the time. So we had 5 potential contributing factors. And how do you choose a starting point when you're faced with something like that? Well, we made an educated bet. We ruled out, initially ruled out those first 2 things. We didn't believe that it was essential complexity in the incident to have exactly that particular kind of RAID array failure and the kernel marking things as read-only. So if we're going to reproduce this outage in a local setup, we're going to focus on these next 3 things, at least to begin with. We also, much more temporarily, sort of didn't think about that last one for now. And the reason for that was laziness, really. We want to focus on things that we know how to do, and I was pretty sure I could make those 2 things happen. So we focused there first. And to do those, we turned to everyone's favorite fault injection tool. It's something you know well. It's probably something you've used this week. It's the UNIX kill command. It is the simplest and most frequently used tool for injecting faults into systems. And to make it easier and quicker to run experiments, we were using a Docker Compose-based setup of the same 3-node Postgres cluster, which we could run on our laptops or on some other machine and batter it over and over and try and figure out how to make it fail the way production did. So relatively easy to simulate the failure of the primary. We just used the sig kill. This is kill-9. And we matched what happened on the replica by sending a sig abort to the specific sub-process that crashed on the synchronous replica. So, well, that's enough of a reproduction for those 2 steps. And we kept our expectations low. We didn't actually think this was going to be enough, but it was worth trying. We had something to do. And it was the right choice not to bank our hopes on this. This did not reproduce the outage. The cluster didn't break in the way it did in production. So we went back to the list of what we'd seen go wrong, and we brought back 0.5, the weird log line that we'd seen on the replica. So this is where we start to dive a bit more into what the database is actually doing, and try and figure out how we can make Postgres log exactly this thing in our test setup. And I want to talk a bit about the word log, because it actually means 2 different things. We're often used to talking about logs in this sense, like web logs, right? So these could be from someone's blog. What I'm going to talk about now is a different kind of logs. binary logs. And these are used in databases for a couple of purposes. So if we bring in some relatively vanilla SQL, we're inserting 3 users into a table. And at some point, those statements, that data that we're inserting, it has to make it onto a disk somewhere. And if you're back in 2005, then it may end up on persistent storage like a spinning hard disk. Or if we're here in 2023, it's probably more likely a solid-state drive or NVMe if we're getting fancy. And the explanation I'm about to give you of how this happens is a simplified version, but it's essentially true. It covers all of the important points. When you run a query that adds or changes data in a database, the first thing that the database does is it writes a record of that change to disk. This happens before it modifies any of the tables on disk. Postgres calls this write-ahead logs, and a bunch of other databases do as well, because you're writing every change into this log ahead of applying it to the actual tables and indexes. But why do you bother doing that? Why write these down on disk? Well, the first thing is databases need to be crash safe. They need to preserve your data, even if some random thing causes them to crash in the middle of normal operations. And that crash can happen at any time. You don't get to choose that. So if we look at this table, it's likely that we'd have some primary key on the left there, and primary keys have an index, so there's an index pointing at it. Now, in a world without write-ahead logs, if we inserted directly into the table, we hadn't yet updated the index, Postgres could crash. What would your database return at this point if you did a query that was going to hit that index? You were selecting by ID. Well, what would happen is that you wouldn't see that third record because it's not in the index. If you went to look it up, Postgres would tell you, no, there's nothing there, there's no 3. But because we made a note of it in the write-ahead logs, when Postgres starts back up, the first thing it does is play back those write-ahead logs. And it puts your database back into a consistent state and lets your queries return consistent data. The other thing that write-ahead logs get used for is replication. And if you remember our setup from earlier, those replication streams that I pointed out are fed by the write-ahead logs. So now we have at least a high-level understanding of what this is saying. So we try, the replica booted back up, it tried to apply some write-ahead log, and it failed. And something, just to point out where this comes from, is with Postgres you can have an archive of your write-ahead logs. This is used if your node has fallen behind, or if you're bootstrapping a new node, this is quite useful to have. What we didn't understand is why would this failure of restoring a write-ahead log cause the synchronous replica to be promoted? To fail to be promoted. The frustrating thing about that was the synchronous replica already has all of the writes. It's the synchronous replica. It doesn't need to get any more data. So we were confused as to why it would see this log that it had pulled in and be unable to start because of it. But when you're debugging something, this is like the most important thing, I think, to keep in mind, which is that just because something shouldn't happen doesn't mean it didn't happen. So we had to follow this lead and either confirm or disprove it. There was just one thing staring me in the face when I looked at this error message. And I mean staring me, Chris, personally in the face. Which is that at the time of this in my career, I'd had 0 experience working with binary formats. I'd been able to ignore it. I'd been able to go, yeah, Postgres does this stuff, and that's great, and I trust it. So I had to go and dive into something uncomfortable, but ultimately none of what's going on is magic, right? It's just more code written by someone else that does something that's a bit unfamiliar to me. And the nice thing is we can cheat. Postgres is open source, so we can go and look at the code. We're not having to do anything, we're not having to do as much guesswork. But everything I'm about to show now also works on closed source software. Like, you can do this if you don't have documentation about the file formats. We just have a different word for that, reverse engineering. So thankfully, open source software is great, and we can gret for the error message we saw. And we get 3 hits. And if we dive into the first of those, we see a relatively simple conditional. We've got some guard check there, and we've got report invalid record, which is just logging the error that we saw, and it jumps into some error handler. What we need to do to make this happen is make this conditional evaluate to true. We don't know what these two terms are yet, but we can figure that out by jumping through more source code. Size of xlog record is just a constant. It is defined as the size of some struct in the Postgres source code. And that's just going to be the same value for some particular version of Postgres. So if we can make the other variable, total len, equal to 0, I would bet that's going to be smaller than the size of any constant, or of any struct, rather, because they're going to be bigger than 0. So it turns out we don't have to go far to find total len. It's a field on the struct, in fact, on the xlog record struct. And if we look there, it is the first field on that struct. So that's the thing we're going to have to modify at some point. So if we've got all those pieces from the code base, how do we tie them together in the actual binary log files that we have on disk? That code represents, or is how that log file is produced on disk. So if we go back to that, what it's saying is relatively simple. If a log record says that it is smaller than the smallest possible size that a log record can be, it is invalid. That is obviously an error. So if we take those insert statements that we had before, let's look how those insert statements turn into binary logs in Postgres. If we run this again against the Postgres instance in our little Docker Compose setup, we can grab the binary WALs produced from that and load it up in a hex editor and be smacked in the face with a barely comprehensible wall of data. What we're looking at here is a representation of that binary stream of data in hex and ASCII, wherever ASCII characters are available for it. It's just the same data rendered differently. It's all just numbers, it's just bytes. However you want to look at it, these are all fundamentally the same thing. And we're going to be focused on hex and the ASCII representations, just because that's what you see in a hex editor. And the first and most obvious thing that leaps out is some good news. We can see those values that we inserted, Cod, Loveless, and Turing. In all of that is that xl.len field, the total length field that we want to find. How might we go about finding that in a big binary stream? What could we do to influence the stream in a way that makes it easy to find that field? Well, if you're trying to find a size field in a binary stream, if you produce data that increases in size by 1 at a time, all you're looking for is something that is incrementing within the hexadecimal or ASCII. So we just look for a field that's increasing by 1. And so we run it again, except with these inserts instead. You can see the data we entered, and now we need to look for the incrementing field. And now I was a little bit sneaky with this table. I chose this bit of the ASCII table very deliberately, so we can see the data we inserted, and we can see part of that ASCII table from earlier. This is the incrementing size field, as shown in the ASCII version of things. And if we go back to the hex version, we can see the hexadecimal representations too. It's all just the same data, and now we've found that field that we want to edit. So how are we going to go about editing this? The situation we have is we've got 2 Postgres nodes. We've got one of them producing this log, and then through replication, it ends up in the other node. What we need to do is grab that log, do some stuff with it, and then feed it back into the replica. And if we were doing this in production, we'd write some, civilized, nice code to do that. We'd import the Postgres structs, and we'd write some tests, and we'd do all this fuss. But we're doing this on our laptops, and it doesn't matter if this breaks, right? We can just try again. So the actual way to solve this is to write a regular expression in a script that does all of that monkeying around with the data. And if we take that, we need to pick one of them to break. I chose the top one for this example because it's easier to point an arrow on a slide at it. This is the actual script that we wrote a few years ago when we had this. And there is precisely one interesting line. The rest is just reading and writing files. And all we're doing here is doing a regular expression substitution for the known size field and the data, and then replacing the size field with 0. So, are you ready for some exciting computation? There we go. Changed 1 byte of data. And what happens if we feed that into the Postgres replica? Well, we get the error we were hoping for. Success. Feels great for about 2 seconds because it didn't cause the cluster to fail over. Pacemaker did exactly what we wish had happened in production, and this was not enough to reproduce the outage. Changing that 1 byte was not catastrophic. So clearly, these 3 conditions were not enough. We needed to find something else. And I really, really didn't want to try going back to the first 2, particularly the first one, because if that was a firmware bug on a RAID card, I don't know how to tickle that in just the right way to make it happen again. And it was at that point that one of my coworkers, in fact, noticed something. They noticed something that I'd missed while I'd been looking into this. And if we jump back into our architecture diagram from earlier, I mentioned that we had that virtual IP address which was always co-located with the primary node. What we'd added a couple of months earlier in staging and production, but not in the Docker Compose setup, was a second virtual IP address. That virtual IP address was managed, was called the backup virtual IP address, and was managed in the opposite way. It was always on one of the replicas to allow us to take backups more cheaply than we didn't want to put backup traffic against the primary, where all the writes are happening. So this was a little optimization that we'd done, but we hadn't brought it back into our local dev setup. So we had a new lead, but this was very much a surely not in our heads, right? Like we had no hypothesis for why this would cause the failure, but just because something shouldn't happen doesn't mean it didn't happen. Let's carry on with that. We added it into our cluster, we ran the reproduction script, and we watched, and we waited, because it took about a minute to run. But I won't make you wait a minute. It worked. This caused the exact failure that we'd seen in production. But why, right? This doesn't make sense. Having 2 virtual IPs plus those other conditions is enough to make Pacemaker not move things around for us. We spent another day or 2 scratching our heads with this and trying to figure out exactly what was happening here. And it turns out it's related to how Pacemaker schedules resources onto machines. This is its core job. It's quite different to Kubernetes, but you could think of it like what Kubernetes does is also scheduling stuff onto machines. And there are 2 relevant settings that caused this outage to happen. The first thing to keep in mind is that Pacemaker, by default, will reschedule resources with no penalty. It will assume that things can be moved around freely if there's any reason to do so. And this isn't good for databases. You generally don't want to shift your primary around all the time because it will cause even small interruptions to clients. Whenever Pacemaker moves that primary over to another node, we would see a small loss of connectivity. We didn't have any fancy query queuing at the time. We added that later. So we used this setting called default resource stickiness to combat that. All that says is, Pacemaker, if you can avoid moving things around and still satisfy your scheduling constraints, then please don't move things around. The second setting is that by default, resources can run anywhere. There's no preference for resources to run on particular nodes. But we already saw 2 resources, the 2 virtual IPs, that can't work like that, right? We have specific nodes that those need to be on. And Pacemaker has something called a colocation constraint, which is how you solve this. If you give something a positive colocation score, it says, please put these together. A negative score means, please do not put these together. And these are the actual settings from our Pacemaker cluster at the time of the outage. We had a default resource stickiness of 100. We had a colocation constraint of negative infinity between the backup VIP and the primary. And it was the second one that was the problem. And it was that value of negative infinity that was the problem, because there is a very subtle semantic difference between using negative some large number and negative infinity. And this bit us really badly. It turns out that negative infinity is a special value in Pacemaker. If you compare negative 1,000 with negative infinity, negative 1,000 means avoid scheduling these together, whereas negative infinity means literally never schedule these together. Stop the world if there is no other solution. So we ran our test again and changed negative infinity to negative 1,000 in our local Dockerized setup, and failover worked properly, as we had hoped it would on the day. All of that for a few characters of diff. And there's something awkward I have to acknowledge about this talk when we get to this point, which is that the write-ahead log error was a total red herring. Once we had a working reproduction script, we went back to it and tried removing parts of it to see if we had the same failure, but with fewer moving parts. And it turns out that we could remove all of that binary log rewriting. I'm sorry. I know that was the most interesting core part of this talk, and it would have been very cool if that was actually part of the incident. But it was part of the debugging process, and that's what I'm here to talk about. And that's why I think this was interesting, because we have to go through these red herrings, these deep technical sort of ultimately misguided attempts to figure out what's going on the computer to arrive at a conclusion. And it's the process that's the important bit to learn about. So I hope that you're happy that you saw this. And there we have it. The minimal reproduction of that Postgres outage was the hard failure of the primary, the correlated crash of the synchronous replica, that bit was necessary, and the backup virtual IP being located on the synchronous replica. And having gone through the details of that specific incident, I want to zoom out and extract a few lessons before I say goodbye and start taking questions. None of the stack is magic, as I mentioned before. Like, whatever level it is that we work at most days, day to day, you could be a front-end engineer, you might be working on load balancers, you might be working on databases, whatever else. You can always jump down a few layers in the stack if you need to. Like, you're all very capable people. And I think people just generally in industry have this fear of doing this, of just diving into unknown code and exploring and figuring things out. And it's a really, really useful muscle to build. And you've probably heard the adage of the cloud just being someone else's computer. Well, I'd like to twist that slightly and say that other code is just full of someone else's abstractions, right? Like, all of them can be understood and reasoned about because some other human being wrote them. And we often hear this advice to go and read other people's code to learn about how it works and how different people do different things. But I think there's a useful exercise that you can add on top of that, which is having a go at modifying something really unfamiliar, trying to make it break a specific way, or trying to add some functionality into it, specifically in code that you are unfamiliar with and have not been involved in the writing of. The second thing, and this is something that terrifies me to my core, is that automation erodes knowledge. But when we arrived at this cluster, we spent an hour trying to get Pacemaker to work again. And all of that time we were down. But we were all afraid to turn the thing off and manually configure replication between the two Postgres nodes, because frankly, none of us had done it for about 2 years. And game days are a partial fix to this, as long as you're imaginative enough to come up with the scenarios that are actually going to happen to you in production later. I think one thing that's often missed with game days, which I personally have missed many times, is doing game days where you don't know how the problem could occur. So we didn't need to know in advance that Pacemaker could bite us in this particular way. We could have just said, imagine something happens and we need to stand up our database by hand. Let's practice that. That's the game day. Lastly, whenever you're doing something like this, you must always question the reproduction that you're writing. And I'd gone totally sort of down the rabbit hole trying to figure out this binary log thing and getting to my answer. And it didn't help us, ultimately. And it took a coworker tapping me on the shoulder and going, I think you've missed this thing in the local setup. You've got to zoom back out sometimes and think, have I missed some wider context here? So to sum up those, there's no magic in the stack. The erosion of knowledge through automation is scary and somewhat possible to fight. And you should always question the reproduction that you're writing and whether you're focused on the right part. As well as those lessons, I'd like to do a tiny bit of stargazing and be a little bit pretentious here and try and make a prediction. In making a prediction, I'm being a bit cheeky because it's kind of already happening. For the last decade and a half, we've got very used to APIs that look like this, JSON over HTTP. This is what powers many, many systems these days. But my prediction is that binary formats are coming for web development. And really, they already have. A lot of APIs now look like this, protobuf over HTTP2, specifically often gRPC, which is a standardization of that format, released by Google quite a few years ago now. And these are binary formats, both of them. And I think it's going to become more and more essential that people are comfortable to dive into what's going on there because we're going to have incidents involving these. We're not dealing in text-based formats the whole time now. So it's worth getting familiar with them. And I have one last thing to ask of everyone in the audience here. Most computing in the world, most requests or operations served by a computer somewhere happens successfully, even if it doesn't always feel that way. Days like the one I talked through are the 0.00001% of computing. But they're responsible for all the weirdest outages and the most head-scratching puzzles. And those days have an outsized negative impact on ourselves, on our customers, and on the companies that employ us and keep putting money in our bank accounts. And I think it's a shame not to learn from those incidents. Like, how many times have you seen an incident report get published online that looks something like this? We noticed a problem. We fixed the problem. We're going to make sure the problem doesn't happen again. When we publish these formulaic incident reviews, nobody learns anything. Like we're denied the knowledge of what went on there and the possibility of improving our own systems as a result. So I'm going to leave you with what I think are 3 good examples of incident reviews. My slides will be published later, so you can grab the links, or you can take photos now if you want to. The first one is a review of a Slack outage back in 2021. This was caused by overloaded cloud networking and cold client-side caches. The second was from a company called Incident.io. And what I thought was interesting about this is that they talk about how they used some manual mitigation techniques. They literally had someone managing stuff in queues while someone else was figuring out how to fix the actual bug underlying the incident. And lastly, there's a post from, I think actually the same year as our outage from GitLab. This was a really gnarly database outage that GitLab had. And the level of openness was what struck me in this one. So what I'm asking of you is that if you're in a position to either influence the person who's responsible for these decisions on what to publish, or you are that person, please share the difficult stories as well. Thank you.